Now, there are probably millions of these black holes wandering around as the remnants of these dead, very massive stars within our own galaxy. It's very hard to count them because, for the most part, we can't see them. They're black holes. They don't emit any light. So a black hole just wandering around in space by itself basically can't be seen. But there are a small number of black holes that we can see and study in great detail because, just as John Mitchell suggested in 1784, if a black hole has something else orbiting around it, we can infer the presence of the black hole. And in fact, a lot of stars are born in binary systems with two stars orbiting around each other. And if one of those stars should collapse into a black hole, the companion star would then be orbiting around the black hole. So in that case, what tends to happen is that the gravitational pull of the black hole becomes so strong that it starts to pull gas away from the outer layers of that companion star. That gas streams toward the black hole and spirals down into the black hole in what's called an accretion disk. That's a disk of matter that is accreting or falling onto the black hole and gradually building up the mass of the black hole, making the black hole more and more massive over time. And as this gas spirals down to the center here, to the black hole, before it falls into the black hole and disappears forever, the gas gets very, very hot. It emits a tremendous amount of energy in the form of X-rays. And so these systems are called X-ray binary systems because we can spot them with X-ray telescopes. They're very, very bright sources of X-rays, and there are a lot of them within our galaxy. Now, we can use John Mitchell's trick, then, to determine the mass of the black hole by measuring the orbit of the companion star around it. Now, in principle, that's sort of a simple concept, and it's something that, for example, we teach our undergraduates how to measure the mass of Jupiter by actually measuring with our UCI campus telescope the orbits of the moons around Jupiter. If you can measure the speed and the distance of the orbit of a lightweight object orbiting a more massive object, you can very easily determine the mass of the central object just using simple Newtonian physics. So that's something that in principle we can do for one of these X-ray binary systems by determining the orbit of the star around the black hole. So how do we do that? These stars are so far away that we can't actually see them travel in a circle in an orbit around the black hole. But we can still determine the orbit of the star in orbit around the black hole using the Doppler shift. Now, the Doppler shift is something that you're probably familiar with from everyday life. If you ever remember hearing an ambulance coming toward you and you hear the pitch of the siren coming towards you, and then suddenly as the ambulance passes by you, you hear the siren going to a lower pitch. That's because as the siren is coming towards you, the wavelengths of sound are squeezed to shorter wavelengths, to a higher pitch. And as the siren is going away from you, the wavelengths that you hear of the sound are stretched out to longer wavelengths, so you hear a lower pitched sound. And light behaves in exactly the same way. So we can measure the spectrum of the light from the orbiting object, from that companion star. We can spread out the light into its constituent wavelengths from blue to red in a plot like this and measure the amount of energy that we're receiving as a function of wavelength. And when we look at the spectrum of light from a star, any star like the sun, we see these characteristic dips in light in the spectrum. And those dips come from atoms in the outer atmosphere of the star that absorb light at very, very specific wavelengths. It's almost like sort of an atomic fingerprint of the material in the outer atmosphere of the star. And these three spectral lines, for example, are spectral lines that come from calcium in the atmospheres of most stars. Now, if we observe the spectrum of a star that's at rest relative to us, that's not moving, it might look like that. If we compare that to the spectrum of a star that's moving away from us, say at 300 kilometers per second, which seems quite fast, but that's a sort of a normal leisurely speed for a star to be moving, what you can see if you look closely is that these wavelengths are all shifted. They're stretched out to longer, redder wavelengths. That's a redshift of the light, and we can use that to directly measure the speed that that star is moving away from us. Similarly, if we have another star that's moving towards us, the wavelengths of light that we see from the star moving towards us get compressed. They get squeezed to shorter wavelengths. And so we see basically the same pattern of spectral lines again, but the wavelengths are shifted toward the blue end of the spectrum. So with data like this, we can measure very accurately the speeds of stars moving around in the Milky Way, for example, and we can measure the speeds of these companion stars that are orbiting around black holes. And And I can show you just one example of a measurement for such an X-ray binary system. This is one of my favorite ones because I was part of the team that did these observations at the Keck telescope, and it was a really fun measurement to do. This little dot here, this is part of a visible wavelength picture of part of the sky. These are just stars in some little patch of the sky in the Milky Way galaxy. And that particular star, seen right there, is a very faint, inconspicuous star. It's smaller than the sun, and it's less massive than the sun, but it's a tremendous source of X-ray light. So it was discovered to be an X-ray binary star because a normal star on its own like that wouldn't be emitting X-rays. But that particular system is a very powerful source of X-rays. So we went to the Keck telescope, this was several years ago, for this particular object, and over the course of one night, we measured the redshift of the light coming from that one particular star over an 8-hour period over the course of one night, and found that the speed of that star was actually changing tremendously. It was sometimes it was going towards us at about 500 kilometers per second, and then just a few hours later, it was going away from us at 500 kilometers per second. So this is a star in orbit around a black hole with an orbital period of just 8 hours, which is kind of remarkable if you think about it. And the speed of that star in orbit is about 500 kilometers per second. And by analyzing the motion of that star, we concluded that the invisible companion of that star that it's orbiting around must have a mass at least 5 times greater than the mass of the sun. That is 5 solar masses. But we don't see invisible light. We don't see any object that has a mass of 5 solar masses. If there was a normal star there that had a mass of 5 solar masses, it would be by far the brightest thing in this whole field, and it would be very obvious. The only thing that we really know of that can have a mass as big as 5 times greater than the mass of the sun but be completely dark is a black hole. And so we conclude that there's very strong evidence for a black hole in this particular system. And we know of a few dozen of these X-ray binary systems now that have had their masses measured by techniques like this. And typically the masses come out to be in the range of about 5 to 10 times the mass of the sun, sometimes as much as about 15 to 20 times the mass of the sun. And these are called stellar mass black holes because they have masses that are comparable to the mass of a single star, and they come from the collapse of a single very massive star.